So your third unit is divided into three parts. First, chemical sensor. Second, biosensor. Third, ion selective electrode. So for first parts, chemical sensor. Chemical sensors are the electrochemical sensors. The general classification of electrochemical sensors are potentiometric sensors, conductometric sensors, amperometric sensors, chronoamperometric and chronopotentiometric sensors, acoustic wave device, electrochemical impedance spectroscopy. And next is the application of chemical sensors in food and environmental and biotechnology. This is your third chapter, A part. Chapter third, A part, electrochemical sensors and application of electrochemical sensor. B part is the biosensors and classification of biosensor and application of biosensor. Third part is the ion selective electrode. So in last session we will see the first part, electrochemical sensor. We will see the detail in electrochemical sensor for the first video. So the electrochemical sensors, as we define, when the current passes through the sensing electrode, there is a produce the electrochemical reaction take place between surface of sensing electrode. So the electrochemical sensors are classified into potentiometric sensors, conductometric sensors, amperometric sensors, chronoamperometric sensors, acoustic wave device, and electrochemical impedance spectroscopy. Generally, we see the name suggested potentiometric sensor. Potentiometric sensor. Potentiometric sensor, the measurement of potential difference between reference electrode and working or counter electrode. So the basic diagrams or basic instrumentation are same as we earlier seen electrochemical sensor. Cathode, anode. Anode is the positive terminal, cathode is the negative terminal, and here is the porous membrane, and here it is the electrolytic solution. Cathode, anode attached to battery. Here is the electrolytic solution. So in potentiometric sensor, we measure the potential difference between reference electrode and working electrode. So mainly the potentiometric sensors used for detection of pH. So when we measure the pH by glass electrode, in glass electrode it contains AgCl and KCl is the reference HCl, 0.1 normal electrolyte solution in the glass electrode. So it is the standard 0.1 normal solution in glass electrode. When we dip the glass electrode in acidic solution, measure the hydronium ion concentration. So first application of potentiometric sensor, like we use directly in pH. Next application of potentiometric sensors is measurement of calcium in biological fluid, sodium in biological fluid, and other gases measuring the potentiometric sensor. Second, conductometric sensor. As name suggested, conductometric sensor, the measurement of conductance between reference electrode and here conductometric sensor, measurement of conductance between reference electrode and working electrode. Amperometric sensor. Third type of electrochemical sensors are amperometric sensors. In amperometric sensor, there is has two electrodes, one in the cathode and anode and cathode, deep in electrolytic solution. Same, but in amperometric sensor, we measure the current flows between these two electrodes. So this is the classification of electrochemical sensors. Next, acoustic wave device and electrochemical impedance spectroscopy.
That is filled with an electrolyte. A membrane separates the reaction chamber from the medium to be measured. The membrane is made of a superhydrophobic PVDF. It allows gaseous HOCl molecules to diffuse while it repels OCl ions due to their negative charge. The membrane shows a behavior similar to cell membranes of bacteria, for example. When the sensor is immersed in a medium containing free chlorine, the HOCl molecules diffuse through the sensor membrane and are reduced to chloride ions, Cl-, at the gold cathode in the reaction chamber. At the anode, silver reacts to silver chloride, releasing electrons. This results in a current flowing through the discharge system that is connected to the anode and cathode. This current is proportional to the concentration of free chlorine. The current is processed in the transmitter and displayed as concentration in milligrams per liter. When measuring free chlorine, the pH value must also be determined to compensate for the pH dependent, the counter electrode. A DC voltage is applied to both electrodes. The cathode and anode are located in a reaction chamber that is filled with an electrolyte. The reaction chamber is separated from the medium by a membrane. This porous membrane allows dissolved oxygen to diffuse into the sensor. When the sensor is immersed in a medium containing oxygen, the difference in the partial pressure of oxygen between the inner and the outer membrane walls leads to the diffusion of oxygen through the membrane. The diffused oxygen is reduced at the gold cathode in the reaction chamber, resulting in a current flow that is proportional to the amount of transformed oxygen. The current is processed by the transmitter and displayed as oxygen concentration, partial pressure, or percentage saturation. After a certain period of time, a silver bromide layer forms on the silver anode. This layer reduces the effective voltage and thus the oxygen flow, which can lead to measurement error. In applications with high temperatures during cleaning or